On February 28, 1991, this aircraft was during Operation Desert Storm. An American A-10 Thunderbolt II returned to base with a wing shredded by anti-aircraft fire, half a tail missing, and one engine barely functioning. By every aerodynamic rule in the book, that aircraft should not have been flyable. And yet it landed. Visual. Archival footage of damaged A-10 returning to base. That moment cemented the A-10's reputation as a flying tank. But it also exposed a deeper engineering reality. The A-10 was built for a war that no longer exists. Today's battlefield is saturated with long-range surface-to-air missiles, drone swarms, and radar networks that can see hundreds of miles. The original A-10 survives bullets. Modern air defense systems don't use bullets. They use physics, and physics does not negotiate. So the question facing U.S. engineers isn't, can we build a tougher A-10? Is this, can you rebuild a 1970s low-altitude gun platform into a survivable 2030 battlefield system without violating the laws of aerodynamics, radar physics, and thermodynamics? This is the story of the hypothetical A-10X, a flying tank rebuilt for 2030. And the real challenge isn't armor. It's trade-offs. Part 1, the context. Why even replace the A-10? The original Fairchild Republic A-10 Thunderbolt II was designed in the early 1970s for one specific mission: destroy Soviet tanks in Europe. Its core weapon is the Ju-8/A Avenger, a 30mm rotary cannon capable of firing nearly 4,000 rounds per minute. Visual, slow-motion footage of Ju-8 firing, cutaway animation of depleted uranium round. The airplane was built around the gun. Literally. The cannon sits on the center line of the fuselage because the recoil force is so enormous that mounting it off-center would yaw the aircraft mid-fire. This aircraft was optimized for low-altitude loiter, visual target acquisition, heavy armor, short takeoff from rough fields, and that made sense in 1975. But in 2030, the battlefield looks different. Instead of machine guns and radar-guided cannons, we now have long-range SAM systems, networked radar grids, infrared tracking, AI-assisted drone swarms. A modern system like the S-400 Triumph can detect aircraft over 300 kilometers away. That's not a dogfight. That's a geometry problem. And this leads to the first constraint. Part 2, the physics constraint, radar cross-section. Radar works by transmitting electromagnetic waves and measuring reflected energy. The strength of that reflection is called radar cross-section, or RCS. And here's the brutal truth. The A-10 has the radar signature of a barn. Visual. Radar cross-section comparison chart. A-10 versus F-35 versus B-2. Its straight wings, exposed engine inlets, vertical tail surfaces, all create strong radar returns. Now compare that to the Lockheed Martin F-35 Lightning II. The F-35 uses angled surfaces, internal weapons bays, duct inlets, radar-absorbent materials. Its RCS is estimated to be smaller than a golf ball from certain angles. So if you want an A-10X to survive in 2030, it must reduce radar signature. But here's the problem. Stealth and close air support are philosophically opposed. Why? Because stealth requires smooth surfaces, no external stores, internal weapon bays. Close air support requires heavy payload, large gun, external pylons, long loiter time. Every external bomb increases radar return exponentially. Visual, graph showing RCS versus number of external stores. So the first engineering dilemma: do you prioritize survivability or firepower? You cannot maximize both. And that's how the A-10 was reborn for a new era of warfare. Subscribe for more machines that redefine power. Part 3, Aerodynamic Reality, the Low-Altitude Paradox. The A-10 was designed to fly low, very low, below radar coverage. At low altitude, air density is higher, and aerodynamic drag increases with the square of velocity. Drag equals 1/2 rho v superscript 2 CdA. Let's break that down. Rho equals air density. V equals velocity. CD equals drag coefficient. Equals frontal area. At low altitude, rho is high, so to fly fast near the ground requires enormous thrust. And thrust means fuel burn. The A-10's straight wings generate excellent lift at low speeds, which is perfect for loiter. But straight wings increase drag at higher speeds. The A-10's top speed? About 420 knots. That's subsonic. Now compare that to the General Dynamics F-16 Fighting Falcon, which exceeds Mach 2. Speed is survivability, but speed reduces loiter time. Loiter time wins wars in close air support. Again, trade-offs. Part 4, Materials Science. Can we just add more armor? The original A-10 uses a titanium bathtub to protect the pilot. Visual. Cutaway showing titanium armor tub around cockpit. Titanium is strong, corrosion-resistant, and relatively lightweight, but not light enough. Armor adds mass. Mass increases wing loading. Wing loading equals aircraft weight/wing area. Higher wing loading means higher stall speed, reduced maneuverability, longer takeoff distance. If we upgrade to composite armor or advanced ceramics. Ceramics are hard but brittle. Composite armor improves energy absorption but is expensive and difficult to repair in field conditions. And modern threats are no longer small-caliber rounds. They're proximity-fused missiles. No amount of cockpit armor will stop a fragmentation warhead detonating nearby. So instead of armor, engineers shift toward signature reduction and electronic warfare. Survive by not being seen. Part 5, The Engine Problem. The original A-10 uses two turbofan engines mounted high and separated from the fuselage. This protects against foreign object debris, ground fire, but exposed engines create radar and infrared signatures. Modern air defense uses heat-seeking sensors. Jet engines are essentially giant infrared beacons. Visual. Infrared camera footage of jet engine plume. To reduce IR signature, engineers might mix exhaust with ambient air, shield exhaust with tail structures, use adaptive cycle engines. The U.S. Air Force is developing adaptive engines under programs feeding into aircraft like the F-47. Adaptive engines can switch between high-thrust and fuel-efficient modes. But adding advanced engines to a low-cost close air support aircraft, that explodes cost. And now we hit the economic constraint. Part 6, The Cost Reality. The original A-10 cost about $20 million in 1970s dollars. Modern stealth fighters like the F-35 cost around $80 million per unit, excluding lifetime maintenance. Close air support requires persistence. You need many aircraft. If the A-10X costs as much as an F-35, why not just use F-35s? That's the debate happening inside the Pentagon. Visual. Cost comparison chart. A-10 versus F-35 versus hypothetical A-10X. And this is where drone integration enters the conversation. Part 7, The Real 2030 Solution. Distributed lethality. Instead of one heavily armored aircraft, what if the A-10X is actually command aircraft, coordinating autonomous drones, launching precision-guided munitions from distance? This mirrors the concept being explored under next-generation air dominance. The aircraft becomes a network node, not a gun platform. The physics shift from ballistic dominance to information dominance. Part 8, The Trade-offs. Let's summarize the engineering compromises. Add stealth, lose payload. Add armor, lose speed and range. Add speed, lose loiter time. Add advanced engines, increase cost. Use drones, increase vulnerability to jamming. Every solution introduces a new weakness. That's engineering. There is no perfect aircraft. Only optimized compromises. Part 9, The Verdict. Could an A-10X exist? Yes. It would likely have reduced RCS shaping. Use standoff precision weapons. Incorporate advanced electronic warfare. Operate with drones. Reduce reliance on the Gu-8 cannon. But would it be a flying tank? No, because the battlefield no longer rewards armor. It rewards invisibility, networking, and range. The economic reality. Legacy CAS aircraft. And if that happens, the Air Force will ask, why maintain a dedicated close air support airframe at all? Why not multi-role fighters plus drones? The economics may kill the concept before physics does. And that's how the A-10 was reborn for a new era of warfare. Subscribe for more machines that redefine power. Final thought. The original A-10 succeeded because it embraced physics. Fly low, fly slow, carry a massive gun, be hard to kill. But 2030 warfare is governed by a different equation. Not armor thickness, but detection range. And no matter how strong you build the aircraft, electromagnetic waves travel at the speed of light. You can't outrun radar. You can only shape around it. And that may be the final evolution of the flying tank. Not thicker armor, but thinner signatures. Because in modern warfare, survival isn't about absorbing force. It's about never being targeted at all. Because the battlefield no longer rewards armor. It rewards invisibility, networking, and range. The economic reality. Legacy CAS aircraft. And if that happens, the Air Force will ask, why maintain a dedicated close air support airframe at all? Why not multi-role fighters plus drones? The economics may kill the concept before physics does. And that's how the A-10 was reborn for a new era of warfare. Subscribe for more machines that redefine power. Final thought. The original A-10 succeeded because it embraced physics. Fly low, fly slow, carry a massive gun, be hard to kill. But 2030 warfare is governed by a different equation. Not armor thickness, but detection range. And no matter how strong you build the aircraft, electromagnetic waves travel at the speed of light. You can't outrun radar. You can only shape around it. And that may be the final evolution of the flying tank. Not thicker armor, but thinner signatures. Because in modern warfare, survival isn't about absorbing force. It's about never being targeted at all. Electromagnetic waves travel at the speed of light. You can't outrun radar. You can only shape around it. And that may be the final evolution of the flying tank. Not thicker armor, but thinner signatures. Because in modern warfare, survival isn't about absorbing force. It's about never